This is the first of 3 examples classes that I will give you. This one will cover roughly the first third of the material in the course, so I recommend hearing this after the first 5 lectures, covering material up through slide 68 in the lecture notes. There are 14 exercises nominally, but it's really 47 separate exercises because each one has many parts. And of those 47 parts, nearly half of them actually relate to material in the first third of the course, because that's the foundational and conceptual part, which is sort of the sine qua non for the rest of the course. So you'll see we're emphasizing a lot of probability theory here and calculations, manipulating probabilities and entropies, defining entropies, how to understand entropies and how to use them, and some other implications. So this examples class will take almost about an hour, and it covers nominally exercises 1 through 4 of those 14 groupings of exercises. But if you look ahead at exercises 5 and 6 in the second group, in fact, they also pertain mainly to material here in the first third of the course. But I wanted to distribute the load a bit more evenly across these 3 examples classes. I have embedded, in what you see on the screen here, I've embedded, after each of the exercise parts, I've embedded sort of written solutions that make it easier to refer to as we sort of talk through these in the examples class. So let's jump on in. The first part of exercise 1 is about why the information measure is logarithmic, essentially, and you're asked to show that the information measure is additive. That's the purpose of the logarithmic measure, namely show that the information gained when you observe a combination of n independent events, which have these probabilities p sub I going from 1 to n, is the sum of the information gained from observing each one of those independent events separately and in any order. So it's in order to capture desired aspects of independent information, independent events, that lies underneath this logarithmic measure. It is, of course, additive because for independent events, their joint probability of n events is simply the product of all their individual probabilities. So we have this product of factors here, and of course taking the logarithm of any probability, including here this joint probability, it means you could just take the sum of the logs of each of the factors, and this therefore is the information contributed from any given event of all these independent events. So that's how we achieve the desired property of additivity. And that's a straightforward sort of demonstration, and also explains the reason for the logarithmic measure. Then we have some probability calculations in part B, simple, straightforward things just to make sure we understand how entropy relates to probabilities. So 4 rather simple cases. The first one is pixel values in an image whose possible gray values are all the integers from 0 to 255, which is typical for a grayscale image. They have uniform probability, so immediately that tells you how to compute the entropy. It's just going to be the log base 2 of 256 number of possible states. That all follows, as you've seen already, from the basic definition of entropy. And of course, in this particular sub part, each of the pixel values have probability 1 divided by 256. So you have a sum over 256 cases, each of which has the same term in front. It's probability 1 divided by 256 times the log base 2 of that same probability, and that all works out trivially to 8 bits as the entropy for pixel value in such an image. And in fact, when we come to study image compression and coding schemes later on, and protocols like JPEG, the payload of compressed images is usually referenced to 8 bits per pixel as what you would have to do, the price you'd have to pay if you didn't have compression. So 8 bits per pixel is a metric that you'll encounter again later on. Okay, second subpart is humans. It's classified according to whether they are or are not mammals. Well, at the present time anyway, all humans are mammals, so this is a subset of the class of mammals. There's no uncertainty about that classification, and so the entropy is 0 bits. This of course, might change in the future. We may have to revisit this answer if, Elon Musk gets his way and we have some sort of hybrid merger with machines. In fact, they're called cyborgs. That's a contraction for cybernetic organism, and many people are promoting that as the only possible future for human intelligence as AI takes off. And so at that point, I'm not sure that whether this answer will still be correct, because humans may become cyborgs and no longer subsets of mammals. Well, be that as it may, part 3 asks you to envision an insect population which is trisexed. So there are 3 different genders which have these probabilities: a quarter, quarter, and a half. What's the entropy of the question of gender in such a population? Again, straightforward application of the basic definition of entropy works out to 1.5 bits. And finally, the 4th subpart asks about a population of persons who are classified by whether they are older or not older than the population's median age. So again, as in the second earlier subpart, these are classifiers, and of course classifiers build clusters, and those clusters have probabilities of membership or frequency of membership, and therefore we can calculate their entropies. In this case, by definition, a median is that value which divides the population into equal halves as far as possible, so there are as many above as below the median. Therefore, both classes have probability 0.5, so obviously the entropy is 1 bit. Okay, the third subpart of this exercise asks about asks you to compare the entropy of 2 different random variables, x and y. I think I sort of anticipated this exercise in one of the opening lectures. Let's have a look at it. Variable x takes on any one of just these 8 integers, 1 through 8, with equal probability. So this random variable is one of these 8 numbers, with each of them with probability 1/8. However, random variable y can be any positive integer, k, going out to infinity, but with probabilities that follow this attenuating exponential probability distribution, namely 2 to the minus k, or 1/2 to the kth power, is the likelihood of integer k being selected. So 1 is just one of 8 possibilities, that's x, and y can be has an infinitude of possibilities. Which one has greater entropy, or you have more? Which one gives is a question with more uncertainty for you? Calculate both of these entropies and then their joint entropy and the mutual information. Well, the first subpart here is meant to be a bit surprising, although it's a bit too late to surprise you, I think, because it turns out that there's greater uncertainty about selecting just one of the 8 integers with uniform probability than selecting any positive integer with this decaying exponential distribution. And of course, the reason follows simply from those calculations. As you know, variable x has an entropy of just 3 bits, because it's, well, the straightforward application. When n is, each of the probabilities is 1/8, you end up with entropy of 3 bits. But the rapidly decaying probability distribution for any variable y has this as its summation. So this is an average. This is the minus p log p expression, but we want to find out how that averages out. If we take the sum of all such terms out to infinity, that gives us the expected, as it were, the number of questions you would have to ask in the optimal sequence in order to discover which of those infinite possibilities I have selected. So you can think of this as the game of 20 questions extended out to infinity, and the average, the entropy, and therefore the average number of questions you might have to ask, actually is just 2. This limit is known to be 2 bits. On slide 53, I think you saw this limit being invoked. So, in conclusion, there's more uncertainty about choosing one of 8 integers than having to choose one of infinitude of integers when their probability distributions are as specified here. 3 bits versus 2 bits. I hope that might have been at least a little bit surprising at some point in your life. Okay, then the second subpart is about the joint entropy of the two random variables. They are specified as independent random variables, and then their mutual information. Well, because they are independent, we know that their joint entropy is going to be just the sum of their individual entropies. Think back to that Venn diagram with non-overlapping ovals. So we have 3 bits plus 2 bits equals 5 bits. And also a consequence of their independence is that their mutual information is 0 bits because those they don't intersect. The final part, subpart D of this exercise asks what is the maximum possible entropy of an alphabet consisting of n different letters. And in such a maximum entropy alphabet, what's the probability of its most likely letter and of its least likely letter? And finally, to think about why fixed length codes are inefficient for alphabets whose letters are not equiprobable, which can, of course, be discussed in connection with Morse code. Well, as you know well by now, I think the maximum possible distribution of symbols in terms of maximizing entropy is the uniform distribution. So with you get maximum entropy from n letters if each one has probability 1 over n, and then the entropy is simply log base 2 of n, as you've seen already. So the condition of maximizing entropy means this set of probabilities for the n letters, and because they are all uniform, it follows that 1 over n is the probability of both the most likely and the least likely letter, because they're all equally likely. Finally, fixed length codes, of course, are inefficient for alphabets whose letters are not equiprobable, because the cost of coding improbable letters is the same as the more probable ones, and it's more efficient to allocate fewer bits for coding the more probable letters and to make up for the lost address space of such short strings by adding more bits and having longer codes for the less probable letters, as is done with Morse code. As you all know, the letter E, being most common, is coded with just a single dot. And that's the end of exercise 1. Exercise 2 begins with some similar types of questions about probability calculations, in this case inference, as bringing inference into the story. Let's suppose that it's true, and I guess it is true, that women who live beyond the age of 80 outnumber men in the same age group by 3 to 1. Assuming that's true, how much information in bits is gained by learning that a person who lives beyond 80 is actually male? Let's have some shorten the notation. We'll simply write the word old to mean somebody who lives beyond the age of 80. And we have, therefore, the conditional probability. Given that somebody's old, the probability that they are female is 3 times greater than the probability that they're male. That will say given. And of course, it also follows, at least at the present time, last time I checked anyway, that the sum of the probabilities of being male plus being female equals 1. From these two expressions, it follows that the probability of being male, given that somebody is old, is just 1/4. And given that the information measure is simply based on the logarithm of the probability, it follows that the information gained from observing that or learning that a particular old person happens to be male is 2 bits, not 1 bit, but 2 bits, because that conditional probability is just 1 in 4. Next, you're asked to use the independence bound on entropy. Suppose we have n discrete random variables, x sub 1 up through x sub n, and we have an entropy associated with random variable x sub I. So h of x sub I is the entropy of that particular random variable. And one of them is known to be the largest. That's x sub L for largest, and it has a known entropy, the one that's largest among all these random variables. What then is the upper bound on the joint entropy of all these random variables? And under what condition will that upper bound be reached? And also, what's the lower bound on the entropy? So all of this can be worked out just by thinking about the Venn diagram for independent and non-independent events, and thinking about the independence bound on entropy. The upper bound on the joint entropy is, of course, the sum of all their entropies. And that upper bound is achieved only if all of the random variables are independent. So here we have an upper bound for the joint entropy of all those n random variables. And the lower bound, of course, because it's a sum, the lower bound is whatever is the smallest, whatever is the largest. The random variable with the largest entropy is the smallest that this sum could possibly be. Conceivably, the others may all have zero entropy. So this is a lower bound on the joint entropy here, and we therefore have so in other words, the one with the largest entropy is the lower bound on this sum. So we have now two inequalities that we can combine together into one expression. The joint entropy has a lower bound, which is the entropy of the random variable that had the largest entropy, and the upper bound is the sum of all the entropies of those random variables. And that's all just kind of a reflection of the independence bound on entropy and the way that independence is handled for joint entropies being the union of all of those elements. Okay, now part C is asking you to consider several matters related to deterministic functions. Actually, the first four subparts here assume invertibility of a deterministic function. The last two abandon invertibility. So first we assume that x is some random variable which has some fixed entropy of 8 bits, and there is some function, a deterministic function, y of x, that maps x into a different random variable. So, and initially we assume that this is an invertible function, meaning that for each unique value of x, there's a unique value of y. Although this can be any complicated function. It could be some hugely nonlinear monster equation, but initially there's a one-to-one relationship between the values for x and y, and there's a kind of monotone condition. This amounts to a monotone condition so that it will be invertible for the first four subparts. Well, first, what is the entropy of the random variable y? Clearly, it will have the same probability distribution as the random variable x. The values may be radically different, depending on how complicated the function is, but it will have the same probability distribution as each of the values for random variable x. So that's also 8 bits. What's the conditional entropy of y given x and of x given y? Let me just jump ahead to where the solutions are embedded. Because of determinism, both of those are 0. Given that x determines y, the conditional entropy of y given x is just 0. There's no uncertainty left because this is a deterministic function. And given that it's invertible so far, it also follows that there's no uncertainty about x given y, so we have that conditional entropy also being 0. The joint entropy we can calculate in several ways, and since we've got these expressions already, we can just add together the given that the random variable of x is 8 bits plus the conditional entropy of y given x, which was 0. So 8 plus 0, we have this conditional entropy. The joint entropy of x and y adds up, therefore, to 8 bits. Now let's abandon invertibility of the function y of x so that there may be multiple values of x that all produce the same value of y. For example, you would see that in a periodic function. I mean, imagine that y of x is just a sine wave function of x. Then there are different values of x that correspond to the same value of y, and so the distribution of y has lost entropy. It now must have less entropy than the distribution for a random variable x. Now it must be less than 8 bits because you have the same state occupied more than once. And it also therefore follows that knowledge of y does not determine x because it's now no longer an invertible function. So the conditional entropy of x given y is now no longer 0 as it was up here in subpart 3. It's now greater than 0. Okay, so that's just exploring some ideas related to deterministic functions and their entropy and the role of invertibility. We come now to some questions related to the notion of distances between distributions that was introduced with the notion of cross entropy between two different probability distributions. We then looked at distances between distributions for different random variables, and then we returned to the distance between two different probability distributions for a given random variable when I introduced the concept of Kullback-Leibler distance. So this is one approach for such a way of analyzing the distance between two distributions for the same random variable, and the first one was cross-entropy. Both of these concepts come up a lot in machine learning. In that context, the important question is how representative of the real world is the training set that you used for in a machine learning application, for example, and that would show up in the generalizability of what you've learned from the training set to a test set, let alone to the whole real world. So that's the main context in which these distance metrics would appear for you. But here, initially, because we were going on to talk first about coding theory and the efficiency of codes, the same metrics are being applied here to the question of coding efficiency and inefficiency. Okay, so we imagine we have a symbol set consisting of here are the 5 Greek letters, alpha, beta, gamma, delta, and epsilon. And let's imagine we have 2 different probability distributions over these 5 symbols. So here are the 5 symbols. Here's one probability distribution that might describe their likelihood of appearance, P of x, and here's a different probability distribution, Q of x. You can see it has a bit more several more have the same, of these 4 letters have the same probability. And let's imagine that we have 2 different coding schemes, C sub 1 and C sub 2. You can see just by looking at the coding schemes that they are instantaneously decodable and prefix codes, so no code word is the prefix to another code word in either one of these, in each of these coding schemes taken separately. But they have different code word lengths, as you can see, comparing C1 and C2. And so we're going to imagine using these coding schemes for these 5 letters, but either in the case that the true probability distribution was used for those 5 letters, or an incorrect probability, a different probability distribution actually describes the appearance of those 5 letters. So you can see how this is related to the notion of generalizability between training data and test data or real world data. So there are several subparts here. The first part simply says calculate the entropy of each of these 2 probability distributions, P of x and Q of x, and the relative entropies. As you know, these are generally asymmetrical. So normally these 2 Kullback-Leibler distances will not equal each other. In this particular case, it happens that they do. Entropies are straightforward to calculate. You've done this several times already. So for P, it's 1 7/8 bits, but for Q, it's 2 bits. So it's 5 letters being encoded, but with the entropy as 2 bits, you can almost visually kind of expect that you would have slightly more entropy in Q of x than P of x, because more of these are uniform probabilities, and you know that tends to increase, to ultimately maximize entropy if they can all be uniform. So 2 different entropies, and the Kullback-Leibler distances are also straightforward calculations given these 2 definitions in which the roles of P and Q are interchanged. And in both cases, it happens that the Kullback-Leibler distance works out to be 1/8 of a bit. The next subpart of this question asks to show that the average code word length of coding scheme 1 under P is equal to the entropy, and therefore that C1 is optimal for P, and do the same thing to show that coding scheme C2 is optimal for the distribution Q of x, if that's the true distribution. These are straightforward calculations. Once again, you've done this sort of, well, here it's just we're weighting the code word lengths in bits for each of those coding schemes by the simple probabilities under P. So this is just code word length in bits, 1, 2, 3, 4, 4, times their probabilities of those letters being chosen, 1/2, 1/4, and 1/8, 16th, and they all add up to 1 7/8 bits, which was the same as the entropy that we just calculated for probability distribution P of x. So therefore, we conclude under the source coding theorem that scheme C1 is optimal for that probability distribution P. Same calculation for coding scheme C2. Different numbers are different, but we add the average code word lengths by their likelihoods of being used, and that's 2 bits, which again equals the entropy for Q of x. So we conclude again that C2 is optimal for Q. Now, suppose that we used a coding scheme assuming the wrong probability distribution. So we'll now imagine that we use coding scheme C2 when the actual distribution is P of X. What is the average length of the code words, and how much does that exceed the entropy of that probability distribution? So this is just kind of demonstrating really the source coding theorem, because you'll end up with an inefficient code, and then this KL distance will tell you exactly by how much your code is inefficient. So the average code word length of C2 when the true distribution is P, given the code word lengths that are used for each of those letters in C2, adds up to 2 bits, which exceeds the entropy of the probability distribution, which was 1 7/8 bit by 1/8 of a bit. And that is as expected, because that's the miscoding cost that the KL distance gave us for source coding with the wrong probability distribution. And the same calculation can be done if you use coding scheme C1 with those code word lengths when the actual true distribution is Q of X. Same question, how much does that exceed the entropy of Q of X, the distribution, and this again relate that to KL distance. Same calculation. The average code word length of scheme C1, given those code word lengths and the probabilities under Q of X, adds up to 2 1/8 bit, which exceeds the entropy of probability distribution Q of X by 1/8 of a bit, which is again the miscoding cost predicted by the KL distance for using the wrong probability distribution. So there are just a few simple numerical exercises using those metrics and invoking the what is predicted by the source coding theorem, reaching the lower bound and then exceeding the lower bound when the wrong probability distribution is assumed. Okay, that concludes our second exercise. Now we move on to Markov sources, Markov processes to describe the emission of symbols, for example, into a channel. And I used 3 types of Markov processes in the lecture notes, in the slides. You've not seen this one yet, but it's actually most similar to the to the third of those earlier Markov sources. Remember, the first one was a single state Markov process that just emitted 4 letters with some probability distribution. Then we looked at 2 types. We looked at a 2-state Markov process in which one state emitted just 3 letters and the other state emitted 5 letters. But in each of those cases, for 2 of the letters, when they are emitted, there's a state transition. You go to the other state. And that allowed us to calculate the entropies of the overall process, given the entropies of the 2 source states and the occupancy probabilities, which in that case was possible to compute. The third Markov process that you saw was actually a 4-state Markov process, which had sequence constraints, and you moved back and forth. For any given state, you could only emit 1 of 2 letters. For that reason, this particular 2-state Markov process most closely resembles that 4-state Markov process. Here there are 2 states, and if you're in state 0, you emit a 0 with probability alpha, and you stay in this state, and you keep on emitting a 0 with probability alpha. But in that state, with probability 1 minus alpha, you emit a 1 instead, and then you move into state 1, where the same situation applies. With probability alpha, you emit a 1 and you stay in the same state, but with probability 1 minus alpha, you emit the other symbol, a 0 in this case, you move into state 0. And you can see there's a symmetry with these transition probabilities. So first of all, you're asked to calculate what is the state occupancy probability as a function of alpha. Now, normally in Markov processes, calculating state occupancy probabilities is a complicated matter because you have 3 kinds of states. You have recurring states like these 2, you have transitional states, and you have absorbing states. Well, when you go into an absorbing state, it's like death. You never come back, as far as we know. And so it's much harder to calculate state occupancy probabilities for those in a general situation. But Markov processes are beyond the scope of this course. Here you can calculate occupancy probabilities just from the flow equations, because you are equally likely to make transitions back and forth between the two states, and that makes everything easy to calculate. So in the long run, occupancy of these two states is equiprobable, 0.5 each, regardless of the value of alpha, because switches between the two states are equally likely, and so the flow paths are symmetrical. You never get shunted off to someplace else. What is the entropy of these two states and of the overall entropy of the source? Well, we learned that a multi-state Markov process has an overall entropy that is the weighted average of the entropy of each of the states, weighted by their occupancy probabilities, which conveniently are equivalent in this case. And from the definition of entropy, just in terms of state probabilities, it's easy to calculate that in state 0, with these two probabilities associated with what can happen, we have a simple Bernoulli process. Probability is not 1/2, it's alpha, but still it's a Bernoulli process. And we saw early on that its entropy is this inverted U-shaped function of alpha. So as alpha goes from 0 to 1, it's just a U-shaped curve that rises up from 0 up to a maximum of 1 bit when alpha is 1/2, and then goes back down again. And the overall entropy, of course, is the sum of these two states. Because state 1 is described by the same entropy, so the overall entropy of this Markov process is therefore just this expression. And we would, if we made a plot of the entropy as a function of the probability parameter alpha, we would just get that familiar inverted U-shaped curve peaking at 1. For what values of alpha do both forms of predictability disappear? I should say that in introducing this two-state Markov process, you can consider it to be a sticky oscillator. It's a sticky oscillator because it oscillates between the two states, but if alpha is large, it is sticky. It'll tend to stay in the same state for a long time, so you would get long run lengths of a given bit, like 0 from this state, or long runs of 1s in this state. On the other hand, if alpha is small, approaching 0, then this event is much more likely than this event, so you'll constantly be switching between the two states. It's sort of vacillatory or frivolous, you might say. It's just oscillating all the time. But those are both forms of predictability. Being stuck in one state is a form of predictability, and oscillating back and forth is another form of predictability. And as you know, predictability reduces entropy. And that's why we have this U-shaped curve for the entropy as a function of alpha, whether it's extremely stuck or extremely oscillatory. Actually, Tracy Emmons introduced the concept of stuckist as a description for some of her contemporaries who do contemporary art. If they're stuck in one genre, she calls you a stuckist. Well, here you have. So I'm going to use the word stuckist in the context of this Markov process in the case that alpha is large, approaching 1. In the case that alpha is 1/2, then the process is neither sticky nor oscillatory. It amounts to simply tossing a fair coin, and the two-state process then really collapses into a single state Markov process, and its entropy is maximum at 1 bit per bit emitted. Okay, so that just reconfirms what we've seen about the nature of predictability and its implications for entropy. Now we're going back to the game of 20 questions. In this case, they're just 8 possible letters, and they have a probability distribution, which is that sort of these powers of 1/2. Of course, this would only add up to 1 if the alphabet was infinitely long, and so we'd have this continued series. Here we're stopping with just 8 letters for graphical convenience, and so I have to make the probability of the 8th letter the same as the 7th letter. So both G and H are probability 1 in 128, just so that I can truncate the series, and these will all add up to 1. Now, somebody has selected one of these symbols, and you need to discover which symbol it is by asking yes/no questions that will be answered truthfully. What would be the most efficient sequence of such questions for this symbol set in order to discover the selected symbol in the shortest possible number of questions that are all truthfully answered? Well, for this particular probability distribution, unlike the one that I first used when we first considered the game of 26 questions in this course, here it really is optimal to ask questions like, is it A? No. Is it B? No. Is it C? Etc. Quite unlike the original game of 20 questions. And of course, the reason is that each of these types of questions really delivers 1 bit worth of information, because the two possible answers are equiprobable. The answer yes is probability 1/2, and the answer no is the sum of all these other probabilities, which is also 1/2. So the two possible answers, yes and no, are equiprobable. Therefore, this is an optimal question. It removes half of the remaining probability, and so it's truly a 1-bit question, and that's the optimal question you can ask. We saw in considering the game of 26 questions whether we assumed uniform probabilities or took into account the non-uniform probabilities of the English letters, that the optimal strategy was to group them into sets which added up to total probabilities of 1/2, or successive partitionings of the remaining uncertainty into groups as close as possible to 1/2. And that's why in some cases you could finish the game with just 3 questions if one of the earlier letters was chosen with higher probabilities. Then a very small number of questions would resolve the uncertainty completely. And so this is again the foundation of the source coding theorem. And it's just interesting to see that here what looked like initially a dumb strategy is actually the best possible strategy if this is the probability distribution in question. And that's how you can claim, that's the principle you would invoke to claim that your proposed questions are maximally informative, because each one removes half of the remaining uncertainty, since the two possible answers are equiprobable in each such question. So each question is really a 1-bit question. On average, how many such questions will have to be asked before the selected symbol is discovered? Well, we have again this type of summation of terms. With probability 1/2, you're done after the first question. With probability 1/4, you have to go to the second question. Probability 1/8, you have to go to 3 questions. So take the weighted sum of all of these interrogation durations times the probability of having to have so many questions. They all add up to just under 2 number of questions on average. And this, of course, is also, as you might expect, the entropy of that symbol set, because if you do that calculation, which is subpart 4, you've done this many times now, and they all add up. It's the same arithmetic. It's a different equation, but the same arithmetic as in calculating the average interrogation duration, and you end up with the same entropy, and therefore you can conclude that you have reached the lower bound specified by the source coding theorem if you interpret the code words for these different letters as the bits which are set by the answers to those yes-no questions. And that's exactly how to approach subpart 5, construct a uniquely decodable prefix code for the symbol set and explain why it's uniquely decodable. And it has the prefix property. It's uniquely decodable because, well, it's obvious, and the code for no letter is the prefix or part of the code for, yes, it's not the prefix of the code for any other letter. Here I've changed the code words from what was used in one of those Huffman tree slides in the lecture notes. In that case, I built the code words with the bits reversed. Here, I've just changed I flipped the zeros and the ones so that in the more conventional way, you can interpret a 1 as the answer yes to a yes-no question, and 0 as a no. So this is the sequence of no's, no-nos before you get to the yes. So it's just easier to understand that the bits in these code words in terms of the answers to such yes-no questions. But this is still just a Huffman tree, similar to what you saw in the colored slide. And so I've already talked you through part 6 about relating the bits in the prefix code to the yes-no questions. And finally, we come to one more Huffman tree example in part C. I think this tree also worked its way into the slides. So we have a 5-letter alphabet for which code words have been constructed by the Huffman algorithm. So we have 2-bit code words for letters A, B, and C, and 3-bit code words for letters D and E. And you can see how the branch, each of these virtual nodes is a branching point, and the answer, the branch is determined by the bits which end up being the bits of the code word. So 0 and 0 here become the code word for A, 0 and 1 become the code word for B, and so forth. So looking at just the code word lengths, you're asked to think kind of in the reverse process. Give a probability distribution for the 5 letters that would result in such a tree. Well, in fact, I think it's the same as what I used in the slides, namely these probabilities: a quarter, a quarter, a quarter, an eighth, and an eighth. Calculate the entropy of the distribution and the average code word length for encoding the alphabet. Again, this is now an exercise that's already maybe too familiar to you. So the entropy of the distribution is easy to add up: 2 1/4 bits, and the average code word length, multiplying the code word for each of these letters by the probability of those letters. So 3 then probability 1/4, and those 2 have probability 1/8, and these are the code word length in bits. It adds up to the same total number, namely 2 1/4 bits in average code word length, and that of course conforms with the source coding theorem, that you can build a code whose average code word length comes arbitrarily close to the entropy of the source. You can reach that lower bound typically when the probabilities are all powers of 2, which is why I've tended to choose such simple probability values. If these are not powers of 2, then you get close to the entropy as lower bound, but you can't normally just reach it directly. Finally, exercise 4 begins with a different kind of scenario, but it will end up invoking the same probability distribution. This is a coin flipping experiment in which a flipper, somebody, is secretly flipping a coin until the first head occurs. And X is the number of flips necessary in the run before reaching the first head rather, and then stopping. And again, the flipper will truthfully answer any yes/no question about this experiment, and you want to discover the value of X, the number of flips necessary before the first head was seen, as quickly as possible. And what's the most efficient possible sequence of such questions? Well, it's a different scenario, but the same probability distribution is popping up here. The probability that the nth flip is the one that delivered the first head is of course preceded by n-1 tails. Well, you have n-1 tails, each probability 1/2. It's a fair coin, and 1/2 for the probability of heads. Well, these two probabilities for such a sequence, of course, combine together, and you see that the probability that n was the number of the flip with the first head is 2 to the minus n, or 1/2 to the nth power. And so because the probability is declining again by 1/2 with each successive value of n, we again have the situation that the most efficient series of questions would be: was it on the first flip, on the second flip, on the third, and so forth, because again each of these questions has a probability 1/2 of delivering a yes, and therefore the question is really worth 1 bit. I'm sorry if that's a bit repetitive, and on average the answer will be extracted after only 2 questions have been asked, because the weighted average of the number of questions you have to ask, that's n, times the probability of having to get that far in the interrogation, which is 1/2 to the power n. If you take the sum, this is a probabilities, a weighted sum with probabilities, take the sum as n goes out to capital N, out to infinity, that has a known series limit, which is 2. So once again, the average number, on average, playing that game many times with the person flipping the coin, you would discover the answer after asking only 2 questions, even though it may have taken an infinitude of flips before he saw the first head. So that's again the same sting in the tail, which I hope at one earlier point in your life at least might have been a tiny bit surprising. And this sequence of questions is of course equivalent to a variable length prefix code for X, because for the same reason as we've seen before. Okay, enough of that probability distribution and enough of these guessing games. We turn now to the subject of binary symmetric channels, and the final parts of this exercise relate to first the symmetric channel and then the asymmetric channel. So we have binary inputs 0 and 1 with equal probabilities. That's random variable X, probabilities 1/2 each. And there's an output bits also are zeros and ones, but this channel is noisy, and with probability epsilon, it flips the input bit. So a 0 gets flipped to 1, probability epsilon. Likewise, a 1 gets flipped to 0, probability epsilon. And with probability 1 minus epsilon, each of those two inputs comes out without being flipped. So epsilon is an error probability for this channel, and at the moment, it's symmetrical for the two possible inputs. We're going to change that in the next part. So first, what's the entropy of the source? That's, of course, 1 bit because they are equiprobable. And what's the probability distribution of the outputs? And the entropy of the output distribution? Well, independently of epsilon, it turns out that the output distribution still also has an entropy of 1 bit because regardless of the value of epsilon, the two outputs will appear with equal probabilities, namely 1/2 each. You can see where that's true. The probability of getting a 0 at the output is first the probability that 0 appeared at the input and it wasn't flipped, that's this term, or the probability that a 1 appeared at the input but it was flipped, that's this term. Add those together, you get 0.5, and likewise for the probability of getting a 1 at the output, it's 0.5. So we have the same input distribution, namely the same entropy for the output random variable, namely 1 bit as we saw for the input distribution. Now, a slightly different calculation that you may not have done before is to calculate what is the joint probability distribution for the source and the output, and what is the joint entropy. This is something you may not have done before. Calculate the joint entropy. First of all, we calculate the joint probability distribution by, you can just take the channel matrix multiplied by the marginal probabilities. That would be one way that we used earlier on to arrive at joint probabilities. So this is the probability of 0 at the input and 0 at the output. It wasn't flipped. There's probability of 0 at the input and 1 at the output. It was flipped, and likewise for the other 4 cases. So we have 4 probabilities here for the entries of the joint probability distribution. Calculate its entropy. Well, here's the version of our standard entropy equation for joint probability distributions, P of x and y. And this is a kind of interesting calculation. You can see that of the 4 possible terms that may appear here, 2 of them look like this. Those are the ones that arise if there's not a flip. So from here and from here, there's not a flip, and there are 2 of them. They're the same. So we get this expression, and then the other 2 terms in the joint entropy are the off-diagonal terms. Again, they are they make the same contribution. Namely, in this formula, you have 2 terms that appear like this. Now we can expand each of these. Each of these logarithms is a product of 2 factors. We can, of course, expand that into the sum of the logs for those factors independently. That gives us these kinds of terms. It's all straightforward. Yeah, and using the fact that the log base 2 of 1/2 is -1 makes it trivial to evaluate those expressions, and so you get lots of terms that will cancel out. You see the epsilon here will cancel with the epsilon here, and the 1s will cancel, and so forth. So you end up simply with 1 minus epsilon log of epsilon minus the other one for minus 1 minus epsilon. Now, what does this look like? This is the entropy calculation. This is the joint entropy for P of x and y as a function of epsilon, the probability of a flip occurring in the channel. Well, you can see that it's an inverted U-shaped curve, but its minimum value is actually 1, not 0. If epsilon is either 0 or 1, then the minimum value is going to be 1, because if epsilon is 0, this term is 0 for that reason, and this term is 0 for this reason. We have the log of 1. So if epsilon is 0, it evaluates to 1, and if epsilon is 1, it also evaluates to 1, because this term will be 0 for that reason, and this term will be 0 for a different reason. So the minimum of this inverted U-shaped curve is 1 bit. Its maximum occurs when epsilon is 1/2, because then this is minus 1/2, minus 1/2. So you get 1 minus -1/2 minus -1/2. That's 1 plus 1 equals 2. So here you have an inverted U-shaped curve that rises from a minimum value of 1 at the 2 endpoints up to a maximum value of 2. That's the joint entropy of this particular channel as a function of epsilon, the error probability. Okay, I hope that's clear. And finally, you're asked, what is the mutual information of this channel? Well, we have several ways to calculate that. One way is to use this method. We haven't used this method before, but it's one of the three alternatives for defining the mutual information. Again, in reference to the Venn diagram, it's the sum of the ovals minus their joint, minus their union, with the joint entropy, which we've just calculated, and all three of these terms are now available to us. We know that this is one, and we've just got this expression up here for the joint entropy. Therefore, combine them all together, and we get this expression for the mutual information. And this, of course, is going to be a non-inverted U-shaped curve, otherwise known as a U-shaped curve, because it reaches maximum value well, we've gone through those aspects before. How many values of epsilon are there for which the mutual information is maximal? There are two cases, namely when epsilon is 0 and if epsilon is 1. So either you always flip or you never flip, perfect transmission. In both cases, there's upon receipt of the output, there's no uncertainty about what was the input. So the mutual information reaches its maximum of 1 bit, and that is then also the channel capacity. The next part asks for what value of epsilon is the capacity of the channel minimal, and what is the channel capacity in that case? If epsilon is 1/2, as we've seen before, the channel capacity is minimal, and it's equal to 0, as you can see just from this expression. You have 1 minus 1/2 minus 1/2, it adds up to 0 in the case that epsilon is equal to 1/2. So when flips are equally probable, or when flips are 50-50 likely, this channel is doing you no good whatsoever. It transmits nothing about the input is reflected in the output, and so its channel capacity is 0 bits per bit transmitted. Right. Finally, let's move on to the asymmetric case. An asymmetric communication channel is one whose input source is still the binary alphabet 0 and 1 with equal probabilities, and the outputs are also 0 and 1, but there are asymmetric error probabilities. So a 0 coming in is flipped into a 1 with probability alpha, and not flipped with probability 1 minus alpha, but a 1 is flipped to a 0 with probability beta, and not flipped probability 1 minus beta. So you see the two error probabilities alpha and beta are not equal to each other. And you're asked to do some calculations. First, give the probabilities of both of the outputs, namely that the output is 0 and 1, and those are easy to calculate just by considering the channel matrix with each probabilities. So 0 occurs the probability related to 1 minus alpha plus beta, and probability of 1 is 1/2 of 1 plus alpha minus beta. So you see the signs with which alpha and beta are combined are different for the two possible outputs. And then we are asked to give some values of alpha and beta that would maximize the capacity of this channel, and state what that capacity would be. Well, there are two cases that would maximize the channel capacity, namely you never flip a bit or you always flip a bit, and of course that corresponds to alpha and beta being both 0 or if they're both 1, and in either of those cases the mutual information between the input and the output achieves its maximum of 1 bit, and therefore the channel capacity is 1 bit per bit transmitted. And then finally, maybe the more interesting part of this question is to find all the paired values of alpha and beta that would minimize the capacity of this channel, and then state what that capacity would be. Well, the first part of the answer looks kind of straightforward and maybe intuitively obvious. If both alpha and beta are 1/2, then we're back to the case we encountered in the symmetric binary channel that minimizes the channel capacity. The output is telling you nothing about the input. And also, if you always flip an input, either one or the other, if it's always flipped, then the capacity is minimized, and it's again equal to 0 bits. So basically, this is a case in which what comes out of the channel is always a 0, because 0 gets transmitted without any error probability, but a 1 is always flipped into 0, so you always get a 0 coming out. And conversely here, you always get a 1 coming out, because 0 is always flipped to 1 and 1 is never flipped. And so you're just getting a steady stream of the same value. So you're not learning anything from the channel. It's a dead channel, basically. So in those three cases, for alpha and beta, the channel capacity is 0 bits. And as I said, one of those is something we just encountered in the case of the symmetric binary channel. But there's another interesting case, another combination of values of alpha and beta, which also give you channel capacity of 0. And that's whenever this condition is satisfied, that alpha plus beta equals 1. In other words, the sum of the two error probabilities add up to 1, even though they may not be the same for the two inputs. And interestingly, so now you have a linear trade-off condition between alpha and beta. And if you're anywhere on that continuum of values relating alpha and beta on that linear relationship, then the capacity of this symmetric channel is again minimized to 0 bits. And we've now reached the end of examples class number 1.